Please welcome Serena Kim.
So I'm Serena Kim, and I work right across the street at Steward Observatory. And I forgot to acknowledge here, but this work is related to part of the NASA Nexus team's work called Earth in Other Solar System. We try to understand how the planet-forming disks evolve and what actually is matter for the evolution. So I will continue to talk about when, where, and how planets form. Actually, some of the materials were covered by previous talks, so I think I could skip some of them. So now this is Kepler orrery. There are so far about at least 2,300 confirmed exoplanets. And these actually, here's the solar system orbit. Compared to this, you can see that all these are the exoplanets that are really close to their host star. It's orbiting around, and that's a more massive Jupiter kind. Mercury kind is like a tiny, tiny dot. So you have some kind of idea about there's so many of them orbiting their host star on plane. Okay, let's move on. So stars and planets, they form in dusty, gassy cloud. Meaning, no, I need to actually stop by our galaxy picture. This is not our real galaxy picture, but how we think our galaxy would look like. So our solar system is about 26,000 light years away from the center where our black hole is. There's a bar, and then you can see this fuzzy light stuff. There's a gas, and all these dots and the gas and the stars, actually. If you see that there are some dark spots, I don't know if you can actually see it, but those are dust. They're dust lanes, and there are some kind of reddish things, like beads in string. Those are where active star formation is going on, like young stars. So that's the kind of picture, and that's real picture of another spiral galaxy showing this is the entire galaxy, Messier 83. That's the core at the end of Birch. And here's a spiral arm, and you can actually see dust lane much better for this area. So that these dust and gas is crucial thing for star and planet formation. Okay, so this, I'm not going to talk about this, but I have two hearts in there. I have my heart in this star forming region as well. It's called W345, not very heart and soul nebula, actually. So this is really a lot of massive stars are forming. These are basically young star stellar nursery. It's far away. It's not even in our spiral arm. It's next spiral arm. But this is where a lot of stars actually form, and some harsh environment exists. And that dots, yellow and red and blue, those are the locations of confirmed young stars. So you can have an idea about what kind of stars, where they are formed. Okay, so now I'm going to show you some nebula image that I study. And when you look at this, yeah, I'm sure you have looked at this for many times. Horsehead Nebula in Orion, that's where these look dark because of the dust. There's a massive star, and the UV radiation is actually impinging on this, so we actually see illuminated part and even some evaporation. So that's where young stars form. Another region look like that. So there's a young star here, and jets from young star actually coming out this way. So these are dust pillars where a lot of stars and planets are forming. Now, this look dark, right? So this is dark cloud in optical imaging, the visible light. These are the stars, but this is blocking a lot of background lights. Not only that, something is forming inside and we don't see it. This is infrared light. You actually see the stars inside of the cloud and also the background. So this is a combined image. So these are the dark clouds. Actually, you can see one or few stars forming in here. So now I need to also mention about age. So we know where the locations in our galaxy, where they form. And age of stars, I will skip how we actually measure that. But it is quite difficult to measure the age of the stars. We cannot really start from the birth of the time. Well, I don't have a clock to, I have a clock from birth of the star and then wait until the star dies because they really live long. The shortest one, like really massive stars, would live 1,000,000 years, but 1,000,000 years is quite long for us, right? So what we do is we get snapshot of a lot of young stars to dying stars, and we try to understand the age. So there are many ways to measure the age. I'll skip that. I'm not going to talk about that age. But for stars, if I say 1 to 10 million years, that's very young. They're baby stars. So that's what I'm going to talk about. Even 100 million years is quite young. But given the sun can actually live 10 billion years, and much lower mass stars much, much longer, age is 1 to 10 million is very young. I'm talking about Orion. I'm going to talk about Orion, and that's about 1 million year old. So nurseries. Not only human, but stellar nurseries, they exist in diverse environment. Diversity exists. And environment actually matter. But the question is how does it matter? What do we see observationally? And how can we understand theoretically? That's what our team is doing. So that's a picture of very massive star to very least massive star, M. So the M type is least mass kind of star, and some of them are not even star, they're failed stars, brown dwarfs. Here, I would say a lot of O and B, those are very massive stars, and they actually live very short time, meaning that few million years to 10 million years or so. And they live very, very long. And there are L and T that is missing here, they're brown dwarfs and planetary mass objects. And our star is right here. G2 is our sun. So pretty small, right? And I would call it, if the star-forming region has O star, that's a harsh environment because of output of extreme and far UV radiation. It pours a lot of super energetic photons to the star-forming region. That would be intermediate, about few tens to 100 times weaker than O stars. And then the very weak radiation environment. There are some radiation, but it's very weak. That's what I would define for this talk. And here is Orion Nebula. M42, the Great Orion Nebula, is harsh environment. So our nearest star, Alpha Centauri system, is like 4 light years away. Within there's nothing there between us and that Alpha Centauri system. We have to fly quite far. But for this environment, there's multiple O and B stars. In that distance, there are thousands of stars in it. So it's very dense, and it also has very massive stars. So it is very harsh environment. But this environment is the kind of place that resembles solar system formation. I will keep going for the next. So this is a Running Man Nebula, actually taken by Adam Block in here in Lemon Sky Center. So this is an intermediate UV radiation environment because the massive stars here is the B and later stars. There's no O star in this region. And nevertheless, that has B star, and this is Taurus. So Taurus is a very weak radiation environment. So it doesn't have O and B stars. So harsh environment, intermediate environment, and weak environment, we think they're young planet formation and disk evolution. Disk is where planets form. It could be different. So a lot of people are actually working on the comparison of stellar properties. Okay, so this is Orion. At some point we'll go there, but not yet. Here's the young stars in Orion. It's about 1,300 light years away. If you notice, there's a belt, and there's some fuzzy thing right here, the dagger part. And that's the Great Orion Nebula and Running Man Nebula right here. I actually study all these regions. My group, my students, my postdoc, they all study this very quiet region, very harsh region, and intermediate region as well. So this, if you look at the Orion, that's basically stellar nurseries. Okay, there is one that is dying star on here on the shoulder. It may go away as a supernova, but otherwise, nevertheless, they're very young. This is the region that I'm going to work on, and this is actually called something called Barnett loop, and this is an image using infrared and optical all together. So let's move on. So here we go. So protoplanetary disks. You have seen some of the actually simulation and image from previous talk, and they look like this. These are nearby stars and the disks. So you can actually see these disks in radial sub-millimeter. From ALMA, there's an array of disks in Chile, in Atacama Desert, and they are actually real images. I know you've seen a lot of artist conception. We actually use a lot, and I'm going to show you some later as well, but these are real. What do you see? Here's some gaps, some dark. Here is a gap, and there's some rings. If you see the very bright, the disk is very hot because it's really close to the star, and the outer disks are very cold. And in between, you can see that there are multiple rings. What are they? And the theoretical models actually suggest that these are the places where planets form. And planets can clear out that part of the disk. And here we got some of them spirals, and some of the spirals could be due to the nearby stars. Here is one example of HL tau that has a beautiful face-on disk with some sign of planet. These gaps that can be explained really well by planets. Now that is the comparison of HL tau. HL tau means HL in Taurus. Here is our solar system size. The sun is here, Mercury is orbits right here. So this is actually our solar system up to the outer disk. And here is about the size. So this disk is pretty large. If you remember, Taurus is weak environment. So this will move on about to the dust clouds and disks. What are they made of? How do we know? We image it. We know the size. We can measure the angle of the disk. Sometimes it's tilted. But if we disperse the light from the disk, we can actually see in infrared what they are made of. There's a sign. Here's a wavelength. And here's brightness. And there are some features. These are chemical fingerprints. Some of them are water ice. Here, they appear here. Methanol ice, silicates, and carbon dioxide ice. And these are from, the upper one is from this source. It's a very young star. And this is also another young star, and that has this. So we know there's water ice. Ice meaning that we are getting these signals from the outer part of the disk, because inside, the volatiles will be all evaporated. Okay, now the lifetime matters too. This is another thing, is a whole lecture worth. So the disks last, these gas disks last less than actually 3 million years. Some of them do show in 5 million years, I said it, but mostly 1 to 3 million years. For Orion, we studied that region, even in 1 million years, 20% of the disks have already lost their disks. Meaning that if Jupiter formed, it had to be done by then already. So giant planet formation should happen really, really quickly. Our terrestrial formation can last tens of million years because there are enough materials there. But the gas giants should really form very quickly when the star formation happens. Okay, so this one, you've seen it. I'm so surprised that we actually picked the same kind of figure. This is our solar system. Let's say the terrestrial planets, gas giant, Jupiter and Saturn, and there are some ice giants. Then, of course, we can't miss the dwarf planets. So do not scale this is showing that the size actually comparison. And in this cartoon, the yellow dot is a sun spinning up here, spinning this way, and this is the inner planets. They are all basically in the same plane. In the outer planets, more or less the same plane as well, except the Pluto, and you can see why Pluto is a bit weird. So this is the Neptune over here. And of course, Venus is weird, and that has a different explanation for that possibly. So they all form in plane, more or less. And that's support, actually, the idea that planets form the disk. So I already mentioned the solar system formed near massive stars. So this part goes to where we formed. In our galaxy, I showed you the galaxy, our galaxy, a lot of spiral galaxies, there are a lot of massive stars. And stars form in clusters. Sun must have formed in clusters when it was denser and near massive stars. Now we are kind of alone. It was formed 4.6 billion years ago. Our galaxy is 13.5 billion years. We went around. It lost. It became kind of alone. But solar system formed near massive stars, and that's what we is suggested. How do we know? How do we know that we formed in near massive stars? And that comes from short-lived radioactive nuclides in meteorites. So pristine meteorites, actually. The chondrites, for instance, they have iron 60 or at aluminum 26. It has a pretty much short half-lifetime. It's short enough or long enough in a way. It's about 1 to 2 million years, because that's the actually time scale that disk evolution and planet formation matters. So that's actually pretty good. The lifetime is just right. So these got injected into the planet-forming pre-solar nebula, and we can actually see that isotope ratio studies from these chondrites. We can actually see that these were injected. Some of them could be injected, made in the disk from the cosmic rays, but it is also highly suggested that we really do need some massive stars around. So, massive stars. If you remember, I don't know if you heard about it, we are all star stuff. Other than hydrogen, helium, and trace amount of lithium, they were all made in stars or when they die, right? Stars, very massive stars. Our sun won't die as a supernova, but very massive stars will die as supernova and also create heavy elements. And will not only just create it, they inject their elements into the nearby systems. So they are recycled, actually. And eventually, they come actually to the planets. So this is a cartoon, actually shows supernova explosion in a nearby cloud, okay? And that is an expanding shock. Shock wave would compress the cloud, and all these materials will actually arrive in this cloud. And then these stars form in the dense part of this cloud. And this is a kind of picture. This is a real picture from Spitzer. Came out very pixelized, but this actually is a kind of nebula that you've seen. And these are the locations of triggered star formation, and our solar system formation is suggested such. So it's a triggered mechanism. All right. So here is the part that I would like to actually use a full dome to show, because I want to fly to Orion, and I thought it was a perfect time. Can we do that? Okay, this is Tucson's sky right now. Okay, so when I drive back home, I actually see my favorite star forming region, Orion. I don't know if you've seen it. Can we actually see where the Orion is? Now it's too early, so maybe we can actually. Oh yes, there we go. Yes. So this is Orion, and that was the light's really bright. I couldn't really see it. And that is the belt. And that's where I study. This is where I study as well, about this region. There are some old ones. So we have all kind of stars here. And can you actually point to Taurus? Taurus should be, oops, sorry, it must be quite down. And, oh, there we go. And then actually, if you could actually show the Milky Way. Can we turn that on? So now you see the Milky Way galaxy, the disk part of our galaxy. That's where you can see the dust, right? And that's where stars form. So Tucson is great. You can actually see this really well. So this is a Pleiades. There's a pretty old, is 100 million years or so. 100 million is pretty old for me, but actually it's pretty young for most of the stars. So these are the ones, the very low mass star-forming region, and this one is right here. It's very harsh region, but it has a harsh region and intermediate kind of region, and also quiet region. About this is also pretty harsh because there's all stars there. And from here, if we could fly into the Orion, can we do that, or should I just do it myself? Yeah. So there are other star-forming regions that I skipped, but all these star-forming regions, if you follow this, we can actually find a lot of young stars. So we are flying into Orion. I know we could do that, so I'll need to show this to you. So we know the distance to the stars if we have a spectroscopy kinematic studies. And this is a kind of weird thing going on here. But these are the clouds, Orion cloud. Yep, we can see we're going into the heart of Orion Nebula. So that resolution is, well, we are going to see really good, much better resolution, but this is Orion cloud. So I think we're pretty good. Well, so we'll go back to the Orion Nebula from my presentation from now on. Thank you very much for that show. So, all right, let's go back to my presentation. We were going in the backyard, I was flying. This is actually different wavelength. You don't actually, the sky doesn't really quite look like that. That would be really fun. But we're going there. We just went there. We are going there again, super, super fast. And to the trapezium, the all stars in the middle. This is a Hubble Space Telescope picture. But then we see something else. So my students are working on some of these disks. If you see this sort of dark spot, it looks kind of dirty thing, but that's actually the dust disk around the star. And here's really massive dead Leo star evaporating these clouds away. So you see the tail, cometary shape, and you actually see some of the illuminated part. And inside that cloud, you actually see dust and star as well, star and the disk. So we can actually study interaction from the environment, external environment, to the dust, and then this mass. We can actually study the properties. It's not very easy to know what the center star is, so my postdoc is working really hard on that to characterize the star, and some of us are measuring the mass and the size of the disk. So we're going to some animation for that. So I'm showing you, this is not real. This is animation to just show the dusty disk. And you can see the dust disk just look like one of the disks that I showed you in Orion, and evaporating. And also there's a star over here. We actually see some scattered light, and some of the objects would have jets and outflow going out this way, and disks will accrete. We'll first go to the outer side of the disk. From spectroscopy in infrared, we actually know these sort of what these may be made of. There are a lot of rocks and pebbles, and some of them become big enough, they would call it planetesimals. And these rocks actually are icy because they're outside, it's pretty cold. So silicates, and some of them are maybe like olivine kind, like a greenish, but it's covered with some kind of ice. So these actually get delivered somehow to the inner planets, and they become the source of water on Earth, planet like Earth. Now I'm going into closer to the star. If you remember, I showed you some face-on disk of rings and gas. If you see that there's a gas getting accreted into the star, this is a forming star. It's not burning hydrogen yet. And you can see that there's a planet that's just formed, protoplanet, going around, and it'll clear the disk. What happens is that planets may not only form here, it form out here too, and it'll clear out some part of the disk. So that's what you saw, rings in the real ALMA disks. These are sub-millimeter data. It's quite a while ago, actually. And you actually see the rings of the disk. This is the 100 AU in the solar system comparison. These are larger disks. Because so far, because of the sensitivity issue and resolution, we could first detect bright and large ones. Okay, and this, I show you again, it could be possibly planet formation. There are other explanations as well, but in this case, pretty well explained by planets carving the disk. So here's the cartoon again. The gas, the blue part is a gas, and then the red dots actually represent dust. The star, and at the beginning, these gas actually get accreted onto the star. And these dust, in the end, will settle in the mid-plane. They grow larger. Some of them will bang each other and have some catastrophic event that they will destroy themselves. But unless they do head-on and super fast collision, they will actually get larger and larger and larger. And that rock getting larger, planetesimals, will form terrestrial planets. So these are, and not only that, it will also form accrete enough gas and form gas planet too. Eventually, all these will get thinner and disappear from the actually internal photoevaporation. It will also disappear as well. So this lifetime of disk is about a few million years. And these are the debris disk. We actually have a debris disk, like a Kuiper belt, an asteroid belt. It's a secondary generation of dust. Here are some examples of photoevaporating disks that may be related to our neighbors that long gone. Okay, that's harsh UV radiation. And planets not only form in the disk, it can form itself sometimes. We found, so my postdoc paper here, it looks not very pretty because even though it's not so pretty, the pixelized is actually a Hubble Space Telescope image. It's about 200 AU, and that one has about 10 to 13 Jupiter mass objects. It's a very massive planetary mass. We don't know what it is. It's a candidate planet forming itself. So there may be free-floating planets. Actually, there are a lot of free-floating planets. So that's Running Man Nebula. I'm going there again because I have done some research. But not only all stars, until we have done some study in this region, all these photoevaporating clouds were around all stars, the most massive one, that harsh one that I talked about. But then the theorist suggested me, you should go and look for less massive stars too. And we did. And we found, if you see here, some like a tail going around. This is the B star, actually. And not so pretty image, but these are tail going around here. A tail is blowing away this way. And actually, this arrow points to where B star is. B star is here, and it's actually evaporating this way. And we could measure the size of these and compare to harsh environment. So disks we found here is about 40 to 70 AU. Note that the Neptune is about 30 AU away. Okay. We care about size, but we also care about the mass. So this is the mass of the disks. So it's a dust mass. And I will tell you where the solar system is right here. Here is the stellar mass, and solar system is right here, and we have about 100 Earth mass. So now this is the distribution here, and this is the old so many of the Kepler planetary systems that are measured. And TRAPPIST-1 is right there actually for the mass-wise. So what do we see? We measured the disk in Orion Nebula. The harsh region is about 0.5 to 80 Earth masses. That is not Jupiter mass. It can't form Jupiter. If they want to form Jupiter, it should have already formed within a million years. So disks in Orion Nebula are less massive compared to those in nearby low-density, weak radiation environment like Taurus, for instance. So they're less massive. Size-wise, they're small too. And if Jupiter formed in these disks, they must have formed already. And they are 1 million years old. And here's the size of the disk. And this is our team's work, and the PI is Josh Eisner in our department. And here's the disk radius. Most of the Orion's disk, they're about 20 AU. 20 AU is smaller than the Neptune size. But the distribution, if you see it, some of them are 10 AUs to 50, and most of them are between here, 10 to 30 AU. So 30 AU is more consistent. But we don't see actually that's larger than 60 AU disks, just unlike the nearby stars. These are the heart of Orion, very near stars. Okay, this is disk size. We have compared, I just wanted to show that we compared with other submarine regions. We actually show that this is Orion, and basically they are smaller. So compared to low mass, we are small. We have some measurements. It's from our Allman result by Joe Scheisner and our team. And basically, so the heart of Orion Nebula, very harsh region, disks are truncated. We find that due to UV radiation from our star. And also the density. As I mentioned, the density is pretty high in that region too. And our team's study actually suggests that disks in Orion is less massive and smaller compared to the weak region. And O-star density environment actually do affect disk size and mass and would affect evolution. So in the near future, hopefully, future, we have JWST are going to be launched pretty soon. Actually, these are not happening yet, but being discussed and actually approved. And there's a GMT. Our University of Arizona is partnered. We have like 4 mirrors. The TMT and ERT, for instance, those could actually help us understand this planet formation a lot better. Like this is kind of simulated image, what we might be able to see using those. For instance, much better sensitivity and resolution from Earth and Jupiter, hopefully. So I wanted to conclude here showing you our very special planet. How could we actually have water, right temperature, just right environment? And water, okay, we are trying to understand water delivery. Our team is that actually ties to how in the disk those planet formation happen and how volatiles get delivered onto the stars. So this actually is 7-fold here, and I wanted to end here. So environment matter for the stellar nursery as well as human education, I guess. Thank you.